Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. I am Jose C., the President and CEO of C Squared and Associates Incorporated in the Philippines. We're actually a structural engineering design services firm in the Philippines. And I'm with my colleague, Mr. Ong, who's actually from Asian Institute of Technology, who actually collaboratively did this design for the building. It's a 50-story building in Makati. And it was actually peer-reviewed by Magnuson Clemency. The project is actually located in Makati City. Makati is actually the financial district in the Philippines. It is a residential 50-story building with 3.5 below-grade parking level. The total height is about 167 meters above ground level. It is actually first of the 3 towers on a common podium, and the tower plan is about 35 by about 26 meters. The plan is actually of a reinforced concrete core wall, and it has actually 4 outrigger columns, and the rest are actually gravity columns. And the developer doesn't want any backup frames or moment frames, which will actually obstruct the view of these high-end residential units. So they actually opted for a flat plate post-tension 230 mm thick slabs, and that is the reason why the total seismic resistance of this building is actually offered by purely the bearing wall or the core wall system. And that is the reason why we were actually forced by our code to do an alternative solutions or calculations using a performance base rather than the code base. So we actually, since the building is actually weak in the minor directions, we actually put up 2 sets of BRB located at the, located at the mid-level on the 19th floor, as well as on the 43rd floor of the building. So these are basically the locations of the BRB, which are actually along only on the minor directions, because along the major directions, the y-axis, the core wall are basically long and they're already too stiff. So conventionally, the earthquake resistance system, the seismic energy is actually absorbed by the formations of plastic hinges at specifically designed regions. For example, the base of shear wall and the end of coupling beams. They should be able to deform into an inelastic range and sustain reversible cycles of plastic deformations. With this, the structure may suffer structurally or non-structurally a damage to an extent that it may not be feasible or economical to repair. Alternative to this is to incorporate now energy dissipating devices in the structural system, which will actually dissipate the demand on the other framing system by absorbing much of the energy. And therefore, the structural components of the building may remain elastic during an earthquake so that it may be able to considerably reduce the damage during an earthquake. One of the promising options of these energy dissipating devices are the Buckling Restrained Braces. They are actually widely used in highly seismic region and also for retrofitting old buildings. They are mostly used or widely used in Japan as well as the United States. The components of BRB is basically simple. You got actually the outer tube or the outer casing, and then the inner steel plate, or at times actually a flat bar, at times actually a crossbar. And this inner steel plate, it is actually confined by a concrete, but of course it's actually wrapped by decoupled by unbonding materials so that there is no such thing as a contact between the concrete as well as the inner plate. The reason for this is to restrain now the inner plate against buckling in case that inner plate is actually subjected to compression load. Therefore, how the BRBs work, the axial load is transmitted by the steel core only. Casing, through its flexural rigidity, provides the lateral support against buckling of the inner plate. And that's the reason why if you actually take a look at the properties of these buckling restrained braces, it is basically equal, both for tension as well as in compression. We did the usual process in doing the performance base by actually making use of the guidelines on tall buildings, we actually check the performance of the buildings against a frequent service earthquake, that is, has a return period of about 43 years, which the objective of which is to remain essentially elastic without damage, and can be immediately occupied after an earthquake. And then we have also the design-based earthquake, which is actually the code-prescribed response spectrum, which is actually has a return period of about 500 years or 475 years. And then the maximum considered earthquake, which has a return period of 2,475 years, wherein the objective is basically just a collapse prevention. So the overall design process is you do a code-based design, preliminary design, by way of coming up with the preliminary sizes of your members as well as the size of the BRB. And then you evaluate it against a service level earthquake of 43-year return period, wherein essentially everything should actually remain elastic, and then the building should not actually sustain any damage, which can actually be occupied immediately after an earthquake. And then also at the MCE level, or the maximum considered earthquake, a 2,475-year return period, the building should not actually collapse. So preliminarily, we are actually elastic response spectrum analysis in accordance with the code. The problem in the Philippines is that we're still actually stuck with the UBC 1997. We cannot actually move from UBC to IBC simply because there is no available spectral acceleration map in the Philippines. No government agency actually did this, and therefore, for every special project like this, the developer is actually forced to hire site-specific consultants to do a probabilistic site hazard study in order to establish all these parameters needed for us to do the IBC as well as to do the ground motion, the MC, the nonlinear time history analysis. The site-specific response spectrum for dB levels used, and then approximate sizes of BRB are actually sized, and the structural components to be remain elastics are designed by applying the appropriate amplification factor. A service level evaluation, wherein it has a return period of 40 or 50 years, story drip, coupling beams, and shear walls has to be checked. Required capacities of buckling restrained braces are determined so that they remain essentially elastic under the service level earthquake. At MCE level, nonlinear response time history is actually conducted, and we actually use 7 pairs of site-specific ground motions with 2,475-year return period. And the average of demands from these 7 ground motions approach is actually used in the final analysis of the building. The preliminary design is modified as required in order to meet the acceptance criteria. Coupling beams, core walls, flexural response, and buckling restrained braces are checked in anticipations of nonlinear response, while core wall shear. Diaphragm, basement walls, foundations, and columns are checked to remain essentially elastic during this nonlinear response history analysis. Acceptance criteria, the story drip is actually limited to 0.5%. The coupling beams, shear strength to remain essentially elastic. Core wall flexure should be elastic. Core wall shear should be elastic. Column elastic. And BRB should also be elastic. This is actually at service level earthquake. At MCE level, the story drip is actually increased about 3%. The coupling beams rotations, diagonal reinforcement, these are the short coupling beams, 0.06 radian rotation limit. For the long coupling beams, 0.025 radian rotations limit. And for core wall reinforcement axial, rebar strain should be 0.05 in tension and 0.02 in compressions. And for core wall concrete axial strain is actually a 0.004 plus 0.1, etc. And the BRB should actually should be 9 times the yield strain. So they actually essentially plastic. So we now come to the modeling of this building by way of us using the ETABS for the preliminary design, service level check, ETABS also, and then for the collapse check, we actually use the Perform 3D. I now call on my colleague, Mr. Ong, just to give you the evaluations results as well as the techniques that we actually use in modeling this building.
Thank you. Good afternoon. I will continue the analysis, modeling, and design procedures of this building. For finite element modeling of the building, we used the three-dimensional model, including the tower and the whole podium. For nonlinear model for MCE level earthquake, we used Perform 3D, and we modeled the nonlinear response of the fluctual response of the shear wall and slender coupling beams and short coupling beams, as well as the slab outrigger beams, and also the axial load response of the BRBs. For buckling restrained braces modeling, we use the BRB compound element from Perform 3D. In Perform 3D BRB compound element, there are three parts. The first part is the inelastic portion of the BRB, which consider the inelastic deformation. And second part is the elastic bar basic component, which is the outside of the yielding zone. And then the last one is the stiff end zone, which consider the gusset plates and the end zone of the BRB. And for the coefficients of R, omega, and beta for the buckling restrained braces, properties are supplied by the BRB supplier, Star Seismic Incorporated. For the effective length of BRB, we use 70% of the total pin-to-pin BRB length for the inelastic behavior. This is the backbone curve force deformation relationship of the BRB. For shear wall modeling, we use the fiber modeling technique. In Perform 3D, there is a shear wall element which consider the fiber modeling technique. We use two layers of fiber sections. First layer represents the uniformly distributed reinforcement in the shear wall, the vertical reinforcement. And second layer consider the boundary zones reinforcement plus the concrete section. For the shear behavior of the shear wall, we model as the linear. There are two types of coupling beams in the building. One is the slender coupling beams, which the span over depth ratio is more than 1, and another one is the short coupling beams, in which the span over depth ratio is less than 4. For the short coupling beams, we use the diagonal reinforcement. For long coupling beams, we use conventional longitudinal reinforcement. For nonlinear behavior of these beams, we use the shear hinge at the middle of the short coupling beam. And for the conventional long coupling beam, we use the moment curvature hinges at the ends of the beams. For the flat slab, PD slab in the tower, we do not model by the shell element. We use the frame elements, which is called the slab outrigger beams. We calculate the effective width of these slab outrigger beams using ASCE 41 supplement documents. For the slab outrigger beam nonlinear behavior, nonlinear flexural behavior, we model the flexural hinges at the ends of each beams. For the diaphragm effect of the slab, we consider that as a rigid diaphragm. For foundation modeling, we consider the soil structure interaction effect. We model the retaining walls in the basements as a linear shell element, and the surrounding soils we model with the nonlinear soil strings. But we do not consider the damping effects of the soil. For the boundary conditions, at the base of the core wall, we model as a pin support, while the columns are modeled as the fixed support. These are the classifications of the actions of each structural members. For the reinforced concrete columns, for the axial flexure interaction behavior, we consider as the ductile behavior. For the shear, we consider as brittle. But for expected behavior of these RC columns, we expected the linear elastic behavior we expected. For RC shear walls, for the flexure behavior, flexure action, we consider as ductile, while the shear action we consider as brittle. For flexure action of the shear walls, we modeled as nonlinear behavior. For RC coupling beams, for deep coupling beams with span over depth ratio less than 4, we model as the ductile behavior in the shear action, with the, and also we allow the yielding in these coupling beams. For the slender coupling beams with L over D greater than 4, we also consider as ductile for the flexure response, but for the shear, we consider as brittle and we model as the linear response. For the design of BRBs, we estimate the initial sizings of BRBs based on the wind and service level seismic demands. For the MCE level earthquake evaluation, after conducting the MCE level evaluation, we adjust the sizes of BRB to control the story drift and other performance. These are the BRB details. For the connection design of the BRB and the other members, we followed the AISC 36005 and ACI 31808. For the gusset plate design, we modeled the gusset plate separately and applied the maximum design yield force of BRB. Then we checked the stresses of the plate. And also we checked the buckling stress of the gusset plate due to the compressive loading of the BRB. Then we checked the steel stress which restrained the gusset plate embedded in the concrete against the shear demand. We checked the steel strength of the studs and also concrete breakout strength, concrete pry-out strength according to the ACI. For the concrete breakout strength and for the concrete pry-out strength, we use the ACI 318 anchoring to concrete chapter. These are the stress checking in the gusset plates. We applied the yield force of BRB 4,500 kilonewton in that gusset plate. And this is the shear stat design. The shear stats embedded in the concrete sections. We checked the capacity of these struts. We checked the entire load part of the force transferred from the gusset plate to the outrigger column. First, we checked the transfer force from the gusset plate to the steel section embedded in the concrete column. Then we checked from that steel section to the concrete column. And also we check the axial capacity of the drag elements which transfer the horizontal component of the BRB. These are the BRB connections at the site. This is the detail of the BRB system. These are the assembly fabrication of, this is the erection of the BRB at the site. And this is the drag element to transfer the horizontal force. From the analysis results, we found that the first mode of the building is about 5.75 seconds in the minor direction, in the X direction, And the second mode is 4.86 seconds in the major direction, the Y direction, and the torsion is 3.77 seconds. For the base shear comparison, we found that the DBE level design base shear is about 3.5% of the seismic weight, and MCE level design base shear is about 7.5 to 7.7% of the seismic weight. It is found that our design base shear is larger than the minimum limit set by LATPS TC 2008, which is 3% of the total seismic weight. And also we found that the nonlinear dynamic base shear is approximately 2 times higher than the design base shear, DBE level design base shear. These are the story shear plots of the building from 7-time history analysis of 7 sets of ground motion. The black one is the average results of the 7 ground motions. Here we can see on the right side of the plot, because of the BRB levels, there are sudden changes in story shear. And this is the story moment of the building about x-axis and y-axis. And this is the story drift of the building. Here we can see all the story drift limits are within the acceptable limit of 3%. And also we check for the flexural response of the shear walls. We check the axial strain in the shear walls according to the based on the acceptable limits. These are on the left side, this is the wall compressive axial strain, and on the right side, this is the wall tensile strain. All the strains are within the acceptable limits. And also we check the ductility of the BRBs, which are within the acceptable limits or not at the very strong earthquake level, MCE level. We found that the BRBs are yielding significantly at the MCE level earthquakes, but their average ductility demand is less than 9, which is the maximum allowable ductility demand, which is mentioned in ASCE 4106. Mr. Joe's AC will continue the remaining session presentation.
Just after the conclude. Anyway, just to conclude, no? So we're saying that the BRB, they're actually a first time used in the Philippines, especially for high-rise buildings. So right now we're actually doing something like about 4 high-rise building, high-end residential buildings also using this BRB. And just recently we just actually completed the retrofitting of the Terminal 1, the airport Terminal 1 in the Philippines, using about more than 150 BRBs. So we're saying that the design and applications of BRBs are initiated into locally structural engineering practice, and they actually lead to a better performance for tall buildings, for reducing base shear and controlling deformations, and the potential for applications of BRB system in the future, high-rise building projects in the Philippines is actually very, very encouraging. Thank you so much.